plus 1 upon s dot d upon d tau of minus g alpha gamma x gamma dot. Okay, so we have these two terms, okay, as a result of this. And then we simply subtract this term from this term. Okay, that is our, and we equate it to 0. So we have one term here, two terms, and one term here, three terms. Okay, and yes, there is one trick here which I must write. Okay, I must write that trick. Do I write it with a red? These tricks, or I write this trick here. Let me write it. It's just a very trivial chain rule of the differential calculus, but in this context we need to write. So let me then, I can use white chalk, but we write it on this side. So d upon d tau of minus g alpha gamma, this is d over dx beta of minus g alpha gamma times dx beta over d tau, and this is equal to what? Del over del x beta of minus g alpha gamma into x beta dot. The point is, if one does not worry about this particular form of the equation, then it's okay. You can just take this minus this equal to 0, and you can say, okay, that's my equation of motion, right? But because we are interested in casting this into this particular form, therefore we do little bit of this. And because this is a universally accepted notation that you write down the equation of a geodesic in terms of the Christoffel symbols. That's the reason that we are doing these manipulations. So we make use of this chain rule of differential calculus, and then using this, then this, so using that particular here, okay. A few things I have learned from Germany, and they are very tricky things. You write some equation here, and if I write here, then I'm making use of that here. Do you also do that in Brazil?
Yeah.
Oh, okay, okay. And I have, at least to my students, I have taught them these tricks that are frequently used in Germany, right? So, but as a young student, what I used to do, I used to give the equation numbers to all my equations, and then I used to write substituting this into this, we get this, etc. But here it's a smarter trick. You give the equation number or some symbol there, and you write this, which means making use of this or substituting this back here. It's very, very good, very convenient. So this, these are, so where am I going to use it? Okay, I'm going to use it here. Okay, this we want to make use here. Okay. For this, we want to make use of this thing here. Let me not rewrite it here. But now let me tell you. You can just put it back there, and now can I take another 5 minutes? Okay. Lambert also okay with you?
Yeah.
Okay. We just maybe we try to see if we can complete it. So because these mathematical expressions are in front of us, okay, so we don't need to rewrite them. And I am also in a hurry to start with proper string theory. So these are all supporting material to take us to up to the airstrip where we can take off. Okay, so good. So now I consider a very special case of this general example, and what we obtained for a particular case would also hold true in general. Okay, that's what we would claim later. So what we want to do is we want to take a special case of we want to take a consider a special case s equal to tau, then s dot would be 1 and s double dot would be 0. Okay, s double dot would be 0. So and s dot would be 1 and s equal to tau. We just take simplest possible thing, and but it would hold true in general for all values of s. So if we do this and so we take this term minus dy dt of this term, which means the and we put it back here, everything. Then I think I now really need to perhaps I can remove the upper two lines. Okay, let me not yet remove this, but let me remove this. Okay. So we start from here, and what we have is and we are making it for the case s equal to tau, s dot equal to 1, s dot equal to 1 and s dot equal to s double dot equal to 0. So we want to reduce this equation to this form. Okay, so this term would then drop out because of s double dot. This term would drop out. Here s dot would become 1. This would also be, this is what? This is equal to, this is 1 upon 2 s dot. This is equal to, this is equal to 1 upon 2 s dot into del over del x alpha of beta gamma into x gamma dot. And now this I would put s dot, I would put equal to 1. So now, and for this term I would be making use of this chain rule. For this term d over d tau of this I would be using this. Okay, so I collect all these things back here, and then what do I get is the following: g alpha gamma x gamma double dot plus del over del x beta of g alpha gamma into x beta dot x dot gamma minus 1/2 or minus 1/2 of del over del x alpha of g beta gamma into x beta dot x gamma dot. So one term, another term, and another term. Okay. Now, if we have done that correctly, then I can remove all these things from here. And then we can proceed with this. Okay? Right? So I do that. Hopefully we have not made mistakes, but if we have, we will catch it. Okay? We should be able to catch it. Mathematics is such a beautiful thing. If you make a mistake, you catch it also very easily. No, this cannot happen. Because your common sense is the guiding principle that tells you, no, you have made a mistake. So, okay, fine. Now, here, this particular term I write as 1/2. This is another trick. If you like, 1/2 of del L over del x beta of G alpha gamma plus 1/2 of del L over del x gamma G alpha beta. So, and rest of the things they stay there, these two terms and minus that term. Now I want to combine these three terms together into a Christoffel symbol. I want to combine these three terms, and this is obviously 0 on the left hand side. So I have it here. This is G alpha gamma x gamma double dot plus 1/2 into, if you like, let me write it like del beta G alpha gamma